Okay. Okay, so now do I have everyone's homework assignment? Okay, so thank you for turning it in. I wanted to say that by and large you guys did very well on the homework assignment. Usually homework one is typically where I have to spend a lot of time explaining to people, kind of reiterating what my expectations, but by and large you guys did very, very well. Very few comments that I had to make. Excellent performance. I think it was the highest overall median score on homework one I've ever had in the class, so I'm very happy with that. Yes, you can applaud yourselves. Or not, whatever. I did good. Make sure you submit them. There's still 3 students who didn't submit, so make sure you submit these every day. These are pretty valuable in helping you keep up and be able to develop a method for keeping up. Today's class, we're going to go over reduced instruction set computer versus complex instruction and design principles really briefly, and then we're going to go over computing performance. But first, I need to make a correction. I made a mistake on example 1.4 that I need to correct. I think I've gone too. No, I haven't gone too far. There we go. Okay, so example 1.4, it was the question about finding race conditions and correcting them. So this is the given Carnot map, and I incorrectly in class made did this. I extended this out one further. That is not permitted because the number of p subcubes in any subgrouping, so these are known as p subcubes, these the red, blue, and green here. They have to be some multiple of 2. So that was a mistake that I made, and so I have redone the problem. I'm not going to ask you to resubmit it, but you should keep this in for so that way when you're doing this in the future. So this is a correct way to do this. So one way is you can add another p subcube here, where you have C, D naught, and A. Here, this would be the black one here, and therefore we are now none of them are no longer disjoint. Doing it this way, these are now the reduced equations, and as a result, this was the resulting equation. So this one, the red was A C naught or A C D naught. The green area is A D naught. The blue area is C D naught B. And the black area is C D naught A because I made that little stretch at the bottom. So that's one way of doing it. The second way of doing it is to take the red region and to extend it so that way it encapsulates these 2. So you got to say it has 6, so it meets the proper definition of p subcubes. And therefore the red region is now A C naught D naught, or C naught or D naught. Yes.
Also, the package you track even when you're talking about.
Sure. Hold on. Let me.
Just like I don't want to be trying to review right there, so 1.30 or something.
There we go. Is that better?
Yeah. Yes, sir.
All right. Scrolled down. My apologies. Okay. So now, the key thing is what you're able. If you do this properly, all of the equations should fall in. So does anybody have any questions on that?
You had 2 terms that were the same in the first equation. You had A C naught D naught and C D naught A, I believe.
No, A C naught or A C D naught. You're talking about this one?
You have A C D naught and C D naught A.
A
The
C.
second and the last term on the first equation are the same.
What do you? I'm sure I could reduce it more. I don't understand what you're saying here.
A C D naught and C D naught A are the same term. They're just different orderings.
What A C D naught?
A C D naught and C D naught A.
Yeah. That's the second term and the last term.
Okay, well I didn't reduce it. Now why is it not reduced? Okay, so basically I could delete this. Hold on. So I could just get rid of that. All right, so it's already there because it's
I mean, that's the same equation you had before you applied the correction.
C D naught A C naught D naught, or A C D naught, right?
So the red region should just
Remember,
be
these
A
are-
C naught.
It should be C naught A for red. What do I have? Oh. AC naught. Anything else? Yes.
On the second example, can you explain how you got the or condition for A, C, or D?
No, it's C naught or D naught.
Yes.
So over here, basically you have to figure out the covering. So it's A is the one, and then all the thing that all the other variables on this row here have in the P subcube is they're either C naught or D naught. This 1 is the only one that doesn't have instances in the red, correct? So that's how you get C naught or D naught.
Okay.
So that's just a reduced. Does that what I just say make sense? Any other questions? All right, let's move on. Okay, so we're starting talking about the difference between reduced instruction set computer and complex instruction. Hey, what do you have a question? Okay, sorry, I just hear a lot of whispering in the back. All right, so reduced instruction set computer is kind of what MIPS is, and the whole idea is that you have these fixed instruction lengths. In the MIPS in architecture we're going to cover in this course, the fixed instruction length is 32 bits. Therefore, it has a simpler, limited number of addressing modes and instruction types. And specifically in MIPS, there's 3 instruction types: R type, I type, and J type. And it can be executed in a single cycle, meaning that all of it can be executed between every clock pulse. So you design the length of the clock cycle to match the length of the instruction. And so there's different types of instructions. So a load store length would be longer than just an addition type. So you want to make sure that the cycle and conflict for the longest possible instruction type. So when we're comparing this to a complex instruction set, you have many more instructions. There's basically in reduced instruction set computer, you're trying to take advantage of addition and subtraction to do division and multiplication algorithms, or you're trying to basically use compiler-driven encoding of the microengine to reduce the number of addressing modes and instructions you require. For a complex instruction, you can have many more instruction types. You would require more hardware, so you'd be using different floating point instructions. You'd be trying to use different multipliers, adders, load stores, all simultaneously. And this is why you have variable instruction lengths, meaning that in MIPS, it's going to be 32 bits all of the time. Other times, you're going to have instruction lengths that may require 48 or 64 instruction bits based on the amount of information. So if you're doing, let's say you're doing an addition of 3 variables, A plus B plus C equals F. And you get an instance where in MIPS, you have to add 2, store it in a register, and then add the third one, and then store the result in the register correlating to F. In a complex instruction set, you can actually change the length of the instruction for add 3 instruction, where you would have a third register being referred to in the instruction. So therefore, the instruction would be a little longer, and you'd be accessing 3 registers at once, or 3 registers to do one instruction.
Just cut down on the steps.
Yes. Of course, the issue, so what are some of the pros and cons of these approaches, do you think? So, for example, we're teaching MIPS in this course. Why do you think I would choose MIPS to teach in this specific course?
This is pretty broad architecture.
It's pretty broad architecture, yes.
Fixed number of.
It's fixed. It's simpler. So if you're choosing it to try to teach undergraduate students, throwing a complex instruction set architecture to undergrads can be pretty rough. So we're going to do MIPS. But let's say I was a designer as well, why would I want to choose RISC over CISC or CISC over RISC? What would be some of these trade-offs, do you think?
Would MIPS be faster?
MIPS would be faster in certain circumstances. If you have, and we're going to go here later, we're going to be talking about simplicity favors regularity. So if you have a compiler-driven encoding of the microengine where you're using the same instructions a lot, it can be faster. But if I'm taking advantage of the greater hardware, I can get CISC, and eventually we're going to be discussing very large instruction word towards the end of the course. You can get that to actually run faster because you can have multiple instructions going on in the data path simultaneously. So the answer is yes and no. But yes, a couple other hands up.
Is it smaller?
It is smaller. MIPS is smaller. So if you're dealing with somebody who's like, I don't want to pay for, I have either a smaller area or I have to deal with lower costs, then you want to deal with MIPS. Whereas CISC, if you have a larger area, you can take advantage of the opportunities afforded with the variable instruction lengths. Yes?
As far as the test goes, that is important, but how will these be worded? I mean, are they going to be mix and match or?
If I were asking this question, if I were asking about CISC, let me go into Blackboard here. Okay, so I've said. So I word them very similarly to the topical guide objectives. So blackboard.ole-miss.edu. And this is riveting, I'm sure. Oh yeah. Okay, so you could go under content, if it ever decides to go. There we go. For example, topical guide objectives. So this one is TGO 1.27, right? So the way I would phrase it would be similarly to differentiate between RISC and CISC using examples. So in this type of question, I would specifically want you to say fixed instruction lengths, simpler, limited number of addressing modes, can be executed in a single cycle, therefore higher clock frequencies. And when we go into computing performance, to get back to your question you were asking earlier, higher clock frequencies does not necessarily mean faster computing performance. We're going to show a couple of examples of that later. Whereas the examples for RISC would be many instructions, variable instruction length, an instruction takes many cycles to execute. So, does that answer your question?
Essay type.
Yes. So I will typically be asking essay type questions, kind of very similarly to what we do over in class. The exam will be very straightforward. There'll be no tricks. I don't trick. No tricks. So any other questions about RISC versus CISC? Okay. So in that case, these are what are known as the 4 design principles. And so we can discuss these really quick. So this will kind of go into a little further to how you can come up with your own examples that would be correct for RISC versus CISC. Number 1, simplicity favors regularity. This means that if you're using the same code over and over again, and you design your instruction set architecture to be able to use the regular code, that means it's simpler for the compiler. So you want to make sure that this simple instruction set that's used, especially in the RISC, reduces software overhead. 2, smaller is faster, meaning that anytime you have a smaller circuit, it's going to process the information faster than a larger circuit. And if you So, for example, in a trade-off, when we're talking about preventing race conditions, and we're extending the K-map P subsquares to be able to properly account for all of them, it's still logically equivalent, right? Meaning that the circuit that you're coming up with in terms of the equations, they're going to be logically equivalent, but you have a trade-off between smaller is faster or larger prevents the race condition. 3, make the common case fast. This means that if you have something that you use more often than anything else, we were talking about MIPS being load store architectures and then using the arithmetic logic unit to process register operations. So by making the common case fast, what they're saying is we understand that load and store operations take the longest amount of time. So what we want to do is we want to load everything into these fast registers, perform as many operations as we can using the fast arithmetic logic unit by making that the common case, and then only having to store everything into the registers when we're done with it. So that's what we mean by make the common case fast. And then finally, this is kind of the common sense catch-all, good design demands good compromises. So there's pros and cons to everything. We're starting, yes? No, it's okay. I was going to say that, there's no one right answer to everything in terms of trying to decide. Sometimes you try to push for getting a little more money to be able to have a larger chip to be able to do more things. However, that means more power, that means more area, more cost, and sometimes you have to make these choices. So yes.
Just going back to the second bullet there, you would have to, in most cases, compromise with a larger chip to those race conditions. Okay.
Yes. And sometimes when you're compromising size versus speed in that case. Yes.
Is the way we eliminate the race condition is that gonna be what determines how big the chip is? Like on the example, I think 1.4, you could just add another 2, or you can expand the 1 down so it gives it an OR. So that would be an example of.
Right. And then you could there's various reduction algorithms. I think you guys are familiar with Quine-Mikulski reduction. Okay. For those of you who aren't, we're not going to go into that in this course, but that's a way you can actually kind of reduce variables. I think somebody asked me earlier in last class about if you actually derive the equation from the K-map, do we need to reduce it? And I said no, because on an exam I only have a certain amount of time to ask you a certain amount of things. And if you can show me you can derive the K-map, read it properly, not make the mistake I made on 1.4, and properly show the equation, then it's time for you. Then you've demonstrated the knowledge, it's in your head, move on to the next question. But there are other things, and we're going to be going a little later when we start going into VHDL about difference between structural and behavioral coding. And the difference is the structural coding requires a lot more code, but the result is it's simpler for the synthesis tool to make so the circuit will be smaller, it will require less power, and you'll be able to operate it on more, especially when you're putting it onto a Vertex or a Nexus board. Yes?
When you were talking this doesn't really have, so if you were done,
No, I'm done.
Okay. When we were talking about buffers and that bottleneck, I was wondering what the difference between what the caches have to do with the bus.
Okay, so the whole idea, so you're talking about caches and buses. Right. So we're going to be going into that in section 5 in a lot more detail. But the short version is you have the local registers, and then basically you're trying to take advantage of what's known as the principle of locality, which means that certain amounts of code that you're using in. Okay, so sorry I'm calling you out here, but one of my major pet peeves is do not hand in the homework while I'm lecturing. Okay, so that's just I don't dislike you or anything. It's just a pet peeve, Anyway, back to what I was saying. So the principle of locality means that the code that is used. Okay, so just bring it up. Just hand it in this time. But next time.
I just remember.
Okay. All right. So here's my point. Principle of locality. Use code. Elements in the memory tend to be used again, or elements close to each other tend to be used soon. So you try to use the different sizes of locality. So level 1 cache inside of this Everything's grouped together, and it's a little faster. Level 2 cache is a little bigger, but it's a little slower, and so on.
Yeah, L1's in this redundant, isn't it?
Yes, and we're going to be going into cache consistency and dictionary-based protocol, so yeah. Okay. Any other questions? So we're about to move on to computing performance, but does anybody have any questions about anything we covered last class or anything I just talked about with Sisk and design principles? Okay, so computing performance. Recall the final objective of the course is to calculate the computing performance of a basic computing system. This needs to go away. That was the exact opposite of what I wanted to happen. There we go. And so I was like, I believe I was on 29. Yes. Okay, so the key thing I found that students really struggle when they're doing performance questions is that they have a really hard time keeping track of what equations to use in what situations. So this is why I'm kind of going to hammer the definitions of execution, throughput, and you can start seeing here for performance is 1 over execution time. And I'm start really going into what like a cycle per instruction is, like really break it down. And the reason why is because if you remember the units of them, you can actually derive the equations without really having to memorize them. And when you look at the problem and see, okay, this is what's being asked for, you'll be able to derive the equation, you'll be able to solve it without. So most students get hung up on trying to memorize these equations, and the moment something's even slightly off, they freak out. So I'm trying to teach this in a specific way so you can maximize your ability to implement the equation. So the first thing is execution time. The total time required for a computer to complete a task. Okay. And that the units are seconds per instruction. Or sometimes it'll be seconds over I. And the reason I say this is because sometimes we're comparing two programs where all the problem is say is going to be the number of instructions is the same. Second, throughput. The number of tasks completed per unit time, which is instructions per second. Do you want me to move this up to, is that better for those in the back?
Yes,
Okay.
Thank you.
All right. And 3, performance is 1 over the execution time. So the analogy is running a race. If you have high performance, you have low running time. Meaning that if you're running a 100-meter dash and your running time is high, then you would not be considered a good running performer, right? So same thing. Execution time, if your time takes a long time, you're not a good performing computer. And therefore, I've defined that since performance is 1 over the execution time, and we defined execution time as seconds per instruction, therefore 1 over seconds per instruction is instructions per second. So in computing, we define performance as the number of instructions that you can complete, that your architecture can complete in a given time. Yes?
That's supposed to be in the 1.29, right?
Yes, 1.29. Okay. That's because I got rid of a couple of TGOs, so that's 1.29, yes.
on the problem would we see like this computer?
Oh, we're going to be going over. We're going to be up through 1.10 in terms of examples.
Okay.
So we're going to be going into a lot of.
We would see like this computer has
Yes.
5.6.
For example, just we're going to be. I want to let them finish up here, but very brief example. If computer A runs a program in 10 seconds and computer B runs the same program in 15 seconds, state the improvement in performance of A over B. I'll get to your. You have a question? I'll get to it in a second. So, performance A over performance B. So we're trying to get a ratio, right? So we know that the execution time is 1 over the performance, right? So that means that performance A over performance B is equal to the execution time of B over the execution time of A. And since we said that the execution time of program B is 15 seconds, and the execution time of A is 10 seconds, then we develop the ratio of 15 seconds over 10 seconds, which equals 1.5. So when the question is, state the improvement in performance, it's a factor, 1.5. Yes, what's your question?
Is stuff like execution time, does it only consider hardware, or like say that same program, you could write it in one language and it'd be 10 seconds, and another one and it takes
Exactly right.
So it takes that into account too.
Mm-hmm. Yes. All things. If you're running, you can actually get performance metrics if you run it off of a client running for your particular operating system or whatever system you happen to be running your code on. You can see how many cores it's running, how many threads it's running, things like that, and then you can use that to compare execution time. So execution time can be affected by a number of things. It can be affected by the overhead from the operating system. It can be affected by the compiler. It can be affected by your actual processing at the hardware level. So our focus in this course, I think this is the question you're looking for. The focus of scope in this particular course is how does hardware design affect performance? And getting back to the definition of instruction set architecture, where it allows the software and hardware to be designed separately, this means that we design to the instruction set. The software designers are trying to optimize the code to the instruction set, and the hardware designers are trying to optimize the hardware to the instruction set. So in advanced digital systems, we are looking for methods to optimize the hardware to the instruction set.
Is that 1.5? Is that an arbitrary performance factor?
Okay, so
I like to see.
I see.
Yeah.
Okay, so what this means is, remember I said the units will set you free just a moment ago? Execution time is seconds over instruction. So what we have here is 15 seconds is the seconds per program, so it's a number of instructions. The instructions will cancel out because they are the same program. So now we have seconds over seconds. So it's like a scalar in physics. Yeah, it's unitless because it should cancel out. Any other questions? I'll move this up. So can you see in the back? We are just discussing that. So based on performance A and performance B, 1 over the execution time. So that means we get execution time of B over execution time of A. We know execution time of B based on the problem is 15 seconds. We know the execution time of A based on the problem is 10 seconds. So this becomes 1.5. And we're able to do this reduction because since it's the same program, the number of instructions are the same and therefore they cancel out. Any other questions before I move on? Okay, so clock cycle time. Clock cycle time is the time for one clock cycle generated by the processor. Whereas the clock rate is the number of clock cycles per unit time. So 1 gigahertz is the unit of seconds, so that's 1 billion clock cycles per unit time of 1 second. That's what that means. So a clock cycle time is 1 over 10 to the 9. So that becomes 10 to the negative 9 seconds per cycle. So that's clock cycle time. And CPI, this is clock cycles per instruction. When you have a positive edge, so you begin here, and so let's say the instruction takes this long, and then 1, 2, forgive me for the 4, right? So this means that our CPI, cycles per instruction, would be 4. Yes?
How do you go about increasing the clock cycles per, I mean,
Increasing the clock cycles?
yeah.
You mean like if we, well then we would be getting into clock cycle generation, which is crystals, which would be outside the scope of this course.
Okay, so,
Okay, so advanced digital systems, we receive back to the definition, you receive some inputs, and you have some memory states, and you have some outputs. So in the scope of this course, we are receiving a magical clock that is generated somewhere in the computer. Now design something based on that clock that does X.
So we're not worried about where the clock.
Right now, we are not worried about that. Correct. Yes.
So generally, you can increase the speed of the computer by increasing the voltage.
Generally, but eventually you start dealing with overclocking and buffering issues. But correct.
Just out of curiosity.
But we're going to be okay. Let me get because the key thing is what we're going to be going into is sometimes you don't have. We're going to be discussing something called Amdahl's law today, which basically means that improving a section of the computer doesn't mean that you improve the overall performance. So sometimes what you can do is instead of saying I'm just going to overclock this computer, you can actually get a better improvement in performance by improving the floating point instructions by reducing the CPIs for the floating point. And you can actually, the trade-off is actually such that you don't have to change the clock frequency. You can just do that. So a really good exam type question would be, engineer A decides to increase the frequency to 2.6 gigahertz from 2. So I say the computer is 2.4 gigahertz, and I define 4 instructions with their CPIs, right? Engineer A says I want to increase the frequency to 2.6 gigahertz. Engineer B says I can reduce the CPI of floating points from 3 to 1.8 or 1.8 hours. I'm just pulling numbers out. Which one gives me the better improvement in performance? So through your questions, you guys have just actually come up with a really good exam question. So what's your question now?
It's at work. I'll Google it.
You Google it later? Okay. So for this next TGO, what I did is I took all of the different kind of equations that we can use now that we've come up with these definitions that are tying to CPU execution time. So clock cycles times cycle time. So we have seconds per instruction, cycles per instruction. Let's cancel out to execution time. Next, we have CPU clock cycles divided by clock rate. And we know that works because clock rate is just 1 over the cycle time. So we know CPI is cycles per instruction. Times instructions, we cancel that out. We now have cycles. Now we have clock cycle time, which is seconds divided by cycles. Those cancel out. We now have instruction time, and execution time. And then the same thing, because we know that clock rate is 1 over the execution time.
When you said that a cycle time is 10 to the negative 9 seconds per cycle.
Mm-hmm. No. Cycle time is, okay, so you have gigahertz, right? The idea behind gigahertz is that's 10 to the 9 cycles per second. And that is your clock rate. Your cycle time is the amount of time it takes to do 1.
Right. Okay.
So it becomes 1 over 10 to the 9, which becomes 10 to the negative 9 seconds per cycle. Now, these are good questions. I'd rather you asking me to ask these questions now, but before when I was a teaching assistant, people would be asking them after getting their exam back.
So like in a wireless router, I know Netgear makes a model where you have a 2.4 gigahertz and then a 5 gigahertz.
Right.
Where that is increased. What does you said that I think it's the CPI. Does that change as well when you increase the 5
Because when you're transmitting, so you have two. These are really good questions, by the way. So you have where you're transmitting from and your receiver. So the receiver has to know the frequency, and either it's reading 2.4 or 5. There are trade-offs to each. The 2.4, you want to slow it down because of somebody's in the back is laughing.
Excuse me. It's funny because it's so relevant.
It's funny because I'm gonna pretend I don't know what's on your laptop. All right. So anyway, so you have to have trade-offs. We have frequency, lower frequency. You may be able to make it more secure. So that's one of the trade-offs. You can have it go faster. It's less secure, or consumes more power because power is a linear with frequency. So. Does that answer your question, or a little bit? I'm not going to claim to be an expert in specifically why, but I'm making some educated guesses. Now I'm curious what was funny.
No.
No. All right. Yes.
Now, to my knowledge, I think that at a certain point, that's when you increase the power so much. I think if something runs at about 50% is usually the
Bingo. So the key, remember at the beginning when I was showing you this increase in power and it's going all the way to the sun and you had like the hot plate in the nuclear reactor. So part of this power consumption problem is frequency. So sometimes you don't want to increase the frequency because it's going to go over a certain power threshold. So other times you look for other alternative methods such as reducing the floating point CPI or something like that. So here's an example of a problem. A program runs in 10 seconds on computer A, which has a 2 gigahertz clock. Computer B runs the same program in 6 seconds, but requires 1.2 times as many clock cycles as computer A. So we have two different architectures that are running the same program. Computer B requires more clock cycles, but executes it faster. Yes. More power. Now you're connecting concepts. That's good. No, that's good. What is the clock rate for computer B? So we have 2 gigahertz clock for computer A. We know that computer A runs in 10 seconds. We know that computer B, which is a different architecture, runs the same program in only 6 seconds, but requires 1.2 times as many clock cycles. Meaning that we have a faster clock. And let's say it required 100 clock cycles for computer A, that would require 120 for computer B. Does that make sense? So now we have to figure out what computer B's clock rate is. And sometimes this would be good. You can use execution times on specific programs to test to try to figure out how fast your computer is actually running. So we find the CPU time here. We have is clock cycles over clock rate. So we can solve this since we know the CPU time, which is 10 seconds, right? We know the clock rate, which is 2 gigahertz. And we're trying to find the number of clock cycles, right? Because we're trying to compare it to clock cycles here. So even if we didn't have this equation, let's say we magically, I'm going to scroll down a bit here. So actually, this is about as far as I can go because the people in the back can't see it at all. But let's say I only know that I'm trying to get to clock cycles, and I have 2 gigahertz, and I have 10 seconds. So gigahertz is cycles per second, right? And I have 10 seconds, right? So even without knowing the equation, we know that we can cancel out the seconds, from like stoichiometry back in high school or middle school chemistry. So cycles per second, we multiply it by seconds. Now we have cycles, right? So that means we multiply 10 seconds times 2 gigahertz, which is 2 to the 9 cycles. So 2 times 10 to the 9 cycles. And so now you can either have 20 times 10 to the 9 or 2 times 10 to the 10 cycles. So now that's how many cycles computer A took to execute this problem, right? So this program. So the next part of the problem is we know that computer B required 1.2 times as many. So what do you think we do next? Multiply by 1.2, right? So clock cycles B is just 1.2 times 20 times 10 to the 9, which becomes 24 times 10 to the 9 cycles. So now that I have the number of cycles and I have the execution time of computer B, can I find the clock rate? Yes, because we have cycles and we have seconds. So now cycles per second is our clock rate. Cycles per second, we have cycles, we have seconds, just divide, which is precisely what we do here. So 24 divided by 6 becomes 4 times 10 to the 9 cycles per second. So computer B is running at 4 gigahertz. Yes?
As far as today's technology, what becomes the limiting factor in these?
You mean in the advanced digital section, what are the limiting factors for frequency? Okay, so interconnects, power. So interconnects meaning you have these buses that go between, and I think somebody was asking a little bit about like level 1, level 2 cache. Yes. So the idea is you have to transmit information. Significant amount of power is consumed between these interconnects. As much as, I want to say, I read one paper about a month ago that said up to 47%. So that's one limiting factor, is these interconnects. The second thing is being able to actually consume a certain amount of power. You don't want to put this on your lap and have it burn, or you don't want to have a situation where it's consuming so much power that you're not able to run other tasks. Because power costs, as you can tell when it's plugged in.
What about as far as materials go? I know.
Okay, so just go a little bit. This is slightly outside the scope of the course, but the idea is you want to make sure that you want to be able to maintain the integrity of the signal. And so sometimes when you're sometimes you have to use buffers at those interconnect stages to restore, because the signal begins to degrade a little bit. And it's harder and harder to keep the integrity of the signal the faster the clock rate goes. Because you have to get from 0 to 1. We're in advanced digital systems, so this is actually a very relevant question. You have to get from a 0 to 1 in a certain amount of time to represent the information if you're switching. So if your frequency goes too fast, before you can get up to about halfway before the next piece of information is coming in if you overclock it, so it never properly gets to 1. So that's a limiting factor. So the actual implementation technology is a limiting factor in itself.
Is that why they want to use like graphene?
Yes.
Conducts a lot faster than.
Correct. And there's also with silicon, you have to in order to jump from a 0 to a 1, in order to change the energy level. I'm getting into quantum mechanics a little bit here. But basically, to move an electron, you have to be able to. The reason why it's called quantum is because you have to move a certain amount of energy in order for it to go at all. It'll either just stay there until it gets a certain quanta of energy, and then it will move up to the next level. Graphene has a significantly lower band gap, which is why it does that. But it becomes harder to differentiate. That's the trade-off.
Okay.
So
is it more expensive than silicon as well?
Right now, yes, because we don't have there's no efficient technology. That's the goal, but not right now. Okay, so back to some more boring stuff, performance type questions. So does anybody have any questions about this? Because I typed it out to try to go into a lot of detail for the specific question, but I noticed how I was also trying to derive it in a way in which when you're on an exam, you can try to do it fast. So we can do this the same way for 1.6. Suppose we have two implementations of the same instruction set architecture. So now instead of two architectures, we have two of the same architecture. Computer A has a clock cycle time of 250 picoseconds and a CPI of 2.0 for some program, meaning the clock cycles per instruction for the program on average 2.0. Computer B has a clock cycle time of 500 picoseconds and a CPI of 1.2 for the same program. So you have the same instruction set architecture. Remember, they're compiler driven. Which computer is faster and by how much? And the hardware is coded. I should explain one thing because I say we have implementations of the same instruction set architecture. So you have two engineers. So the way this could work is you have two engineers, and one of them has designed a hardware instruction set that runs at 250 picoseconds for cycle time, or 1 over 250 picoseconds for clock rate, and the CPI is 2.0. Now, computer B, I run it much faster and I have a lower CPI. So I say which computer is faster and by how much. Somebody was asking me earlier about the 1.5 answer, so we're getting to ratios there. So that's where we're going to be getting to. So clock cycles equals CPI times the number of instructions. So if we have the same program, what does that mean about the number of instructions? They are the same, right? And so CPU time is clock cycles times cycle time. So therefore, N, which is I've just come up with this, is to represent the ratio between A and B. So execution time A over execution time B. So that becomes CPI times I. So CPI of A is 2.0 times I. And then for B, you have 1.2 times I times the clock cycle time, which is for A, 250 picoseconds. And for B, it's 500 picoseconds. Let me scroll up a little bit for the people in the back. And that's how we're able to cancel that out. So what happens is we get a ratio of 0.83. That means that XA is 0.83 times as fast as B, which means that B is faster. So the question, the end of the question here, I should say, which computer is faster and by how much? What I mean is, so if you did it the other way, what you could say is execution time B over execution time A would come out to an answer of 1.2. And since 1.2 would be greater than 1, you could say that execution time B is greater than execution time of A. Both ways are correct. So if I'm saying which computer is faster and by how much, at one point you're going to use some sort of ratio. Is he okay? Are you okay? Yeah. Oh, okay. No, you weren't tired. You looking a little sick. I was making sure you're okay. I swear I'm talking to you. Good. Okay, good. Spoken like a professor who's had a student vomit in his classroom once. So does anybody have any questions on how I solved that problem? Okay. So the next concept we're going to go into is something known as average cycles per instruction. So it is the same units. It's going to be CPI, but this equation is how you can use your multiple instruction types to try to get an average CPI. So you know that in a given problem, let's say you have 1,000 floating point instructions, you have 200 load store instructions, you have 100 instruction memory type instructions, and I'll say branch instructions, 50 jumps, and so on. And you know that for each instruction type, you have a different CPI for each of those, right? And if those of you who don't know what I was just talking about in terms of the types of instructions, we'll get to that later in the course, so I believe button. So, but the average CPI, we use this equation, the summation of the CPI for each one divided by the summation of the total instruction count. So if I have 1,000, I can come up with a brief problem like this. Let's say I have 1,000 floating point instructions with a CPI of 1.2. I have 500 branch instructions with a CPI of 1.4, and I have 250 arithmetic instructions with a CPI of 1.6. So what I would do here is 1,000 times 1.2 plus 500 times 1.4 plus 500 times 1.6 divided by the summation of 1,000, 500, 250 for the number of instructions. And we're going to do an example. I just want to make sure I explain that before you go. Yes?
That's supposed to be TG 1.32.
Is it?
Oh,
Yeah.
Okay. So I'll edit that in the notes here.
I just want to make sure.
No, it's okay.
Black out.
Okay, so that's the equation there, 1.32. So example question 1.7 is an example of how we would actually figure out average CPI.
Can you go back up through just a second?
Yeah, sure. Equation?
Yes, sir.
There you go. Okay, great. So example 1.7, given the following CPI for 3 instruction classes and the number of instructions for each instruction class, determine which of the 2 computers is faster and the average CPI for each. So this is what we're given. So you're given these 2 tables. So CPI for instruction class A is 1, the CPI for instruction class B is 2, and the CPI for instruction class C is 3. And for computer 1, the instruction count, so this is a very basic type problem just to help you understand the process. 2 it takes 2 for A, 1 for B, and 2 for C. Meaning that you can see how the equation's starting to work out. So you can see 2 times 1, 1 times 2, 2 times 2 for the summation of instructions times CPI. And then in the denominator, it's going to be 2 plus 1 plus 2, right? So that was how you get your average CPI. Now for computer 2, 4 requires 4 instructions, but CPI is 1. CPI is 2 here, requires 1 instruction. 3 is 3 again, but for computer 2, it requires only 1 instruction to complete the task. And so to show you the actual solution, let me scroll down just a little bit here. So for computer A, it becomes 2 times 1 is 2, plus 2 times 1, which is 2, plus, so that's 2 plus 2 is 4, plus 3 times 2, which is 6, which becomes 10, right? So 10. And then for B, it's 4 times 1, so then 1 times 2 for B, and then 1 times 3 for C. So this becomes 4, plus 2 is 6, plus 3 is 9. So as you can, if I can screw up here, you see the comparison. What I just pointed out is this calculation and this calculation for A and B. So for the number of instructions for A, the denominator, we just add the number of instructions. So we add 2, 1, and 2. So this becomes 10 divided by 5. So the average CPI becomes 2 there. Does that make sense? And then for computer 2, it becomes 4 plus 1 plus 1, which is 6. We determine the number of cycles is 9. So it becomes 9 divided by 6 is equals 1.5. And so which computer is faster? Yes, computer 2. And by how much? Remember, performance is, yeah, so now we can use, so 2 divided by 1.5. If you put 2 divided by 1.5, my goal in this class is not to test how well you can use a calculator. So if you write down the correct ratio, that's fine. Hopefully you guys learned that in elementary or middle school about how to use calculators. Any questions? What's up?
We weren't allowed to use calculators.
Yeah. All throughout school?
Yeah.
It's a good school, I guess. It was awful. It was awful. You'll be permitted to use non-scientific calculators on my exam. The general rule is if it can store anything that involves a word, I'm not going to permit it. But my job is to test whether or not you can actually come up with the equations and know how the computer works. So does anybody have any questions on this particular problem? Okay, so speed up. So now we're going to go into this concept of Amdahl's law, which I've referred to, which kind of goes into everything you guys have been asking earlier about limiting factors of performance, when you can use certain things, you cannot use certain things. This is where this is Amdahl's law, I would say, is important. You should know this. Okay. So the whole idea behind speed up is the factor by which execution time is decreased. So execution time old divided by execution time new, or performance new divided by performance old. And so Amdahl's law, the execution time is equal to the affected time divided by that speed up plus the unaffected. So in this problem we had earlier, where we had instruction classes A, B, and C, and remember for computer 2, instruction class C required 4 instructions, right? So that affected its CPI and affected the overall average CPI, right? So let's say we've come to the point where we say, okay, running power, we can't increase the power anymore, so increasing the frequency isn't an option. But we have an engineer who comes by and says, well, I can reduce the number of instructions required to execute the C class instructions from 4 to 3. That becomes our affected by the change, and then our speed up is 4 divided by 3, since we're decreasing the execution time from 4 to 3. And the reason I can say the time is because the cycles, the clock rate, clock cycle time, CPI didn't change, just the number of instructions. So the ratio remains correct. But classes A and B were not affected, right? So that becomes your unaffected time. And the important point here is it helps in finding the maximum expected improvement to the overall system when only part of the system is improved. So 1.34, state Amdahl's law using an equation and describe its importance. Describe it using the equation. Here's its importance. And if I can actually state the word for word TGO, that's probably a hint that do you want me to scroll it up a little bit? Okay. Okay, so there's Amdahl's law. Execution time new equals affected divided by speed up plus the unaffected. And it helps in finding the maximum expected improvement to the overall system performance when only part of the system is improved. Okay, so 1.8 is a simple example. A given program's execution time is 100 nanoseconds. The floating point addition, which takes 20 nanoseconds of the program execution, is sped up by a factor of 5. What is the new execution time of the program? So basically, we have 100 nanoseconds total. So I can speed up floating points by a factor of 5. So I'm speeding up this 20 by a factor of 5, right? So by using our equation, our affected is the 20 nanoseconds. The speed up is 5. And the unaffected is the 100 nanoseconds minus that 20 seconds. So that becomes 80 seconds of the other arbitrary instructions which are not affected. And this is why understanding Amdahl's law is important. Because you don't want to be the engineer that says I can change one part of it and you think it changes the entire overall performance of the computing system. So therefore, 20 divided by 4 becomes 4 nanoseconds plus 100 minus 100 minus 20 is 80 nanoseconds. So we are now reduced the overall execution time to 84 nanoseconds. So the overall speed up is 100 divided by 84, which is significantly less than 5. And so that's the importance of nominal law. Yes.
So say we have an employer who says, I want this sped up by a factor of 7.
Okay.
Given the current processing time it takes. And we have this equation, we can figure out what we can get it to.
Exactly. Okay, but next question, that's the next question,
Can
actually.
we learn in this class methods to actually do that?
Yes.
Okay.
Yes, we will. So, for example, the table below shows instruction type breakdown for different programs. So we have compute instructions, load, store, branch, and we've already taken the liberty of calculating the total number of instructions for you. So A, assuming that computes take 1 cycle, load and stores take 2, and branches take 3, find the execution time on a 3 gigahertz MIPS processor. So this is where we can use our average CPI and CPU equations to figure this out. So I know number of instructions, I know the number of cycles, so I know cycles per instruction, because it's given defined cycles per instruction, so branch is an instruction type. And I know the clock cycle time, or clock rate, sorry. I can figure out CPU time. So I know cycles so I have cycles per instruction, multiply that by the number of instructions, so now I have cycles, and now I also have cycles per second, right? So if I divide cycles, so I have CPI, right? And I multiply times instructions, those are going to cancel out, right? I'm going to write this a little slower so that way it actually writes. So now we have cycles, right? And if I divide this by 3 gigahertz, right? This becomes cycles per second, right? Does that make sense? These are going to cancel out. It becomes 1 over 1 over seconds, which is now our execution time. So now that by using our knowledge of that, we were able to derive the equation. So now that just becomes, now we use the average CPI, 1 times 1,000 plus 2 times 400 plus 2 times 100, because that's what the problem gives. And then 3 times 50 for branch, divided by 3 gigahertz. We now get 1.50 times 10 to the negative 6 seconds. So that's our CPU time. Which is what? Find the execution time. So I'll scroll up while I explain what is happening in part B. So there's part A for you in the back. Part B. Assume that computes take 1 cycle. So this is kind of a variant on part A, but we change the number of cycles. What is the speed of a program if the number of compute instructions can be reduced by 1/2? So this kind of alludes to what you were asking earlier. So we do the same thing. Yeah, just transcription error here. So let's just make this 2. And somebody would be so kind as to send me an email reminder that I changed 9B to 2 cycles instead of 10, because that's what that problem has. So what we do here is we just have the same equation, except we divide 1,000 by 2 here. So now we're down to 500. Solve for the same thing. So now we reduce it from 2.15 times 10 to the negative 6 seconds to 1.65 times 10 to the negative 6 seconds. And for those of you in the back, let me scroll up. Maybe I should ask the computer that as well. Here we go. So part B, it's the same thing. What is the speed up of the program if the number of compute instructions can be reduced by 1/2? So the same thing, it's the exact same equation. 1 CPI times 1,000 divided by 2. And then from there, just the exact same calculation. And that's how we're able to get this. So the speed up, so key thing, if you're looking for phrasing and how I phrase it, what is the speed up of the program? So again, if I want that, I want some sort of ratio, right? And so speed up is 2.150 divided by 1.650. And the 10 to the 9s go away because those are inherently obvious. The speed up becomes 1.3. Does that make sense? Yes. You have a question? Yes.
Me.
Yes.
Okay, I'm sorry about you.
No, you.
Yeah. So we have.
I'm sorry. What's your name? I apologize.
Hugh.
Hugh Warren. Okay.
Yeah.
So Hugh, what is your question?
The speed up time is 1.3. How is there a way to break down each instruction set as it refers to like the whole process at CPU time?
Yeah, this is what Part A and Part B were.
In Omnill's law, we have to find the total.
You have a total execution time,
Right.
and you're trying to affect the overall execution time by only changing a part of the computing system.
Yeah.
So this is where Ahmed's law is Part B. So I have the previous I have 1,000 compute instructions that have a CPI that take 1 cycle per instruction, right? So that's how that affects the overall execution time of the original computer. So now the engineer comes by and says, I can get you the exact same result by dividing the number of computes in half. So now that becomes our new execution time. So that's how Ahmed's law comes into play. So this is the last, go away. This is the last example question of section 1. So the homework assignment, and I'm going to type this up for you real quick and then run through the problem, is going to be I believe it's TGO 1.27 through 1.34. And example questions, yeah, here we go. So it's going to be recorded here for you. Homework 3 is TGOs 1.27 through 1.34. And the example questions 1.5 through 1.10. Okay, so 1.10 is a good summation of all of the previous concepts. So we have these instruction set numbers. We have a number of floating point instructions, integer instructions, load store instructions, and branch instructions, and then you're given the CPI of the floating point instruction, load store, and branch. So in Part A, and I'm just going to run through this really quickly, but if you have any questions, I am more than open to review at the beginning of next class. So Part A, how much can we improve the CPI of floating point instructions if we want the program to run 2 times faster? So what they're saying is, can we improve the overall performance by 2 if we only affect the floating point instructions? So basically, what we're saying is, we calculate the total number of instructions required, and it comes out to 8192 times 10 to the 6 cycles, right? Actually, you know what? We're only going to do through 1.9 for the assignment. Don't do 1.10. Because this question requires a lot more time than we have. So we're going to do 1.9. So if you have no other questions, you guys are dismissed. So Cayman and Tamir, Tahir and Taiwan, can you guys come up here, please? And is Ramat or Josh here? Is Josh Boosh here? Of your assignment.